Okay, my goal here is simply to clarify a little bit what we did in the last time, which was the proof of path lifting, and write things in such a way that it becomes visible that we used very little about the interval 0, 1. Of course, this is false when the 0, 1 is replaced, say, by the circle, but still we didn't use that much. Okay, so remember, path lifting told you that if you have a path lifting statement was earlier. It told you that if you have a map which is probably here, yeah, this is the theorem. It told you that if you have a covering map and alpha map 0, 1 to x, and then we know the initial point of a lift, then there exists a lift corresponding to that, and in fact that lift is unique. Okay, and the way we proved it, we used Lebesgue number theorem, okay, to reduce this to a local problem. Let me be clear about it. So what was it that we use? Okay, so there's something else that I have not written here. So let's look at the path lifting proof again. Okay, and if we want to see what we have to do, okay, so we decompose it into closed sets. Not a highlighter but a pen. Yeah. So we decompose the interval J1 union J2 into closed sets, and we have one crucial property of these sets. Okay, alpha of Ji is evenly covered. And let me recall here clearly what is it that enabled us to do that. Here I have my target space, something, let me draw it as the annulus, which is the space we knew for which we actually have a covering. Okay, so suppose we have a circle, or maybe an annulus looks a little, is easier to see the picture. Okay, and I have the interval, and I have a map alpha, okay, which it might be better to write here. Well, there are a bunch of evenly covered neighborhoods. Something like this is evenly covered. Its inverse image might actually be many intervals because alpha may be complicated, but it's an open set. And there is a cover by evenly covered neighborhoods, so its inverse image is a cover of the interval. And Lebesgue number theorem tells you, given any cover, small enough set is contained in some set in that cover, given an open cover, which means a small enough set Ji, as soon as it's small enough, diameter is small enough, it's contained in the inverse image of the evenly covered neighborhood. That's its image is contained in the neighborhoods. Okay, so that is the key point. You can decompose 0, 1 into small enough sets, okay, so that the 0, the significance of 0 is alpha tilde of 0 is given and nothing else. So your original space alpha tilde is 0 is the property. So we'll take our first interval J0 as just 0. So we start with first set. They need not be intervals. It's purely incidental that they're intervals. And what we have is we have connectedness of Jk, which is the kth interval, with the union of the previous ones. Okay. In fact, the union of the previous ones is going to be just this guy, and Jk is going to be just the next interval. So the intersection is a point, and path lifting proofs can just use that it's a point and make life easier, but then you have to do the work later. So one might as well observe that it's only thing you need is the interval Jk intersects the previous ones in just one point. Okay, so we inductively define the lift on this. How do we do this? Namely, given lift, let me give it a name. Its name is alpha tilde. Given alpha tilde restricted to union from I equals 1 to k minus 1 of Ji. Okay, we solve local lifting for Jk relative to, so remember the local lifting problem is for a space relative to Jk intersection the previous guy. I equals 1 to k minus 1 of J. And this is connected. That's what we just commented on. And that's really all you use. So this is connected. So we can solve local lifting to Jk, okay, to get, let's say, alpha tilde restricted to Jk, and by gluing lemma by gluing lemma, alpha tilde is defined on the union I equals 1 to k of ji, because up to k minus 1 it was previously defined, and now we have extended it to k. I should comment here, if k equals 1, this looks like sort of the empty case, so let me change that to 0. If k equals 1, we want to define it on the very first interval. Well, then we still had it already defined at 0. So at this point we already knew alpha tilde of 0. So we are solving local lifting problem given the previous one. Okay, otherwise we could still solve it, the lift would not be unique. But the lift exists and is unique right from the very first one, because again we can take it from 0 to k. We are looking at the union of these. So on J0 it was previously defined and we keep extending it. Okay, so I'm emphasizing this because let me just end this short video with a picture, to which will come again when we deal with homotopy lifting, that this kind of structure is not at all special to the interval. It holds even for the square or cube. Namely, if I have a square, then I can divide it into little pieces. Okay, so these are little pieces, and I can order them. Okay, so that I'll order them 1, 2, 3. I'll draw a bigger picture later. 4, 5, 6, 7, etc. I order them in such a way that the intersection of any one with the union of the previous ones is connected, and that's all I'll need. And so the same proof, the way we have stated it, works perfectly well for the square as well. And the square is, remember, the domain of a homotopy. So we'll look at path lifting and homotopy lifting again, and then we will effectively see this proof once more. Anyway, it is so central that we are done, and after that we can milk it for a lot of nice applications.